All right, can I get somebody confirmation you can hear my audio? All right, I have audio confirmation. So, good morning, everyone. My name is David Rock. I'm here at the University of Maryland in Baltimore, Maryland, and welcome back to Cytometry R. It has been a few weeks, and let me step a little bit back from this microphone, Ken. It has been a few weeks, and I'm excited to get started on a new section of the course. Mainly, we will be focusing in on a lot of the cytometry core topics that particularly relate to spectral flow cytometry. So, even though this section of the course is mainly focused on spectral flow cytometry, a lot of these same topics that we're covering are somewhat applicable when it comes to conventional flow. But in the process, we're going to continue building out those functional programming skills that we have started to gradually accumulate through this middle section of the course, beginning back during week 8 when we were looking at how to build our functions, all the way through last time when we figured out how to grab our data from our gating sets and pass it through all the statistics and all the plotting functions to be able to get back quick summary reports. So when it comes to spectral flow cytometry, the ability to infer whether a particular fluorophore is present or absent on a surface or internally to an individually full-stained cell is directly tied to our ability to both extract and provide reference fluorescent signatures from our mixing controls, both single color and unstained, that will accurately match those same signatures as they are being seen on the full stain sample. So ultimately, these extracted fluorescent signatures end up being combined together in a matrix, which is referenced at the time of unmixing to be able to make these particular calls. So we're basically deconvoluting the total signal into its respective components based on those references that we provide. So when we don't provide an accurate reference, we are not able to account for all that signal, and we end up with what we see as unmixing errors. So over these next 3 sessions, my main goal is to get everybody to have some hands-on familiarity with the little individual steps that are happening within this process, so that what may seem at this time as a black box to many can end up being demystified. Additionally, the toolsets that we will develop will help you potentially may help you find solutions and answer problems that we as a field are still grappling with when it comes to determining what makes a good unmixing control and why some things will work for some panels but not in others is not a solved science. It's something we're definitely still grappling with. How is the best way to figure these things out? So, well, the focus of today is a primary course material, kind of like similar to what we've been doing over the last 12 weeks of the course. I also, for this section, will be providing a lot of additional bonus content in addition to these primary sessions. This bonus content is not so much geared at deep diving the nitty-gritty details, but it's more focused on being able, you want to be able to unmix an R as part of your everyday workflow. These bonus materials will be more in line of following that particular sequence of things to be able to quickly adapt it to your own particular data sets and be able to do that on your own. So, as we've done every week, I've already updated the course repository with all the materials that you would need for week 12. So if you haven't yet done so, please go to GitHub and go to your version of the forked Cytometry in R repository and just sync it in so that you get all those changes to your own version. At that point, you just need to come back to your computer, open Positron or RStudio, and pull in those changes to your local computer. At that point, if you're keeping the same organizational structure as what we've been doing throughout the rest of the course, you'll create a week 12 folder. You'll copy and paste in both the contents of the data folder from your local version of Cytometry in R, as well as potentially the R folder that contains all those functions that we've been building, just so that you can make changes to them without affecting your ability to bring in data next time. And if you prefer a video walkthrough of this, we have one of those videos up on our YouTube channel as well, where you can see this actually happen in front of your screen. So for this particular walkthrough, we're going to be using the SDY 3080 3080 dataset, which is available from NIH's import repository. Normally, I would go to Flow repository, but as many of you have encountered, it has been down a lot in the last year. At Cyto, they mentioned some changes that should make it a little bit easier to work with going forward, but as of the time of this recording, it's not quite up to ready to where we need it to be. So, this particular dataset is one that I generated back in 2023. It was part of the original dataset that was our 2025 cord blood innate like T cell paper. And when I was checking import and checking all the different spectral flow cytometry datasets that were available, this is one of the few that contains both the raw as well as the unmixed FCS files. So we'll be using it mainly because we can see how the different moving pieces when it comes to the signature extraction, but then we can also use it to re-unmix the full stain samples in a couple weeks. So these FCS files, as far as context goes, these are from the 5-laser Cytec Aurora. Raw FCS files are substantially larger than their unmixed counterparts, as we've encountered in previous sessions, as we explore to see how extra columns in the extras matrix end up having additional metadata in both the parameters and the keyword slots. So these are a few of the things that we should keep an eye on as we start. Because these files tend to be so large, we're not able to just send them directly via the GitHub repository. So what I ended up doing was I implemented some cleanup gates, and then I used our downsampling function that we created during the week 10 of the course to basically downsample for 5,000 beads or for 10,000 cells so that those files would be of a good size to be able to share as our dataset. However, if you want to download the files yourself and then work with the full-sized files, the walkthrough and the bonus content will also show you all those individual steps that were involved to get to this point. So, for those FCS files that we're using today, the unmixing controls consist of both a full set of bead single color controls as well as a full set of cell single color controls. Those cell controls were composed of both leftover cord blood mononuclear cells as well as peripheral blood mononuclear cells. So when we are deciding how to subtract out the background for individual cell control, we will need to reference to see which of these two types it is, just so that we're accurately removing the background. So you can find those additional details in the link above. Now, if you want to follow along with your own spectral flow cytometry dataset, you absolutely can. So in addition to the pre-processing steps that we are showing below, you can also check out the bonus material for many additional details that might be useful. One thing that you should be aware of before we get started is a lot of what we're doing for checking against a known reference is using the Lucianaga package, and I wrote that one only having access to the Cytec Auroras at our course, so it hasn't fully been validated for all the non-Cytec spectral flow cytometry instruments. So if you do encounter an issue, it's most likely going to be something probably related to a keyword, so just go ahead and open up a discussion post on the Cytometry in our website, and we can kind of identify what these issues are for your particular manufacturer's instrument, and we can try to implement a quick fix before next week. Additionally, there's an issue on the discussion page today saying they're having some issues reinstalling ggCyto and ggplot. I will look into what the solution for that one is today, but let's keep an eye on it in case it's something that's not just one individual's computer, but if it's ggCyto has broken again and we need to see what's going on there. So, over the summer break, what I ended up doing was partially taking advantage of the open source nature of all these different R packages that we're using, and there have been some issues that we have known about for both Flowgate and Lucianaga R packages, especially when it comes to their ability to rapidly implement things as a regular, consistent part of our daily workflows. So I ended up providing a few additional useful functions that will be shown throughout this walkthrough that should make our lives a little bit easier across the board. However, to take advantage of these functions, we need to make sure we update the packages accordingly. So ultimately, at the end of the day, when we are reinstalling a package, we want to remove the previous version and then install the new one. So that is done in R via the remove.packages function, as we've encountered previously, and in which case you would remove Flowgate and then potentially you would remove Lucianaga. At that point, you would then try to reinstall the new version of the package via remote, or alternatively via the package, which would be either _install or install the variation for pack. So what this would look like at that point for if you're doing the remotes version would be install _github, and you're going for nkinstinct/flowgate. And if you're going for the Lucianaga package, it would be install _github, and then it would be my account /Lucianaga as far as what we're ending up seeing. At
that point, we can go ahead and double check to see what our current package version is, and we can then make sure everything is working properly. One caveat to this is, remember, this everything needs to be the newest version of ggplot2 and the newest version of ggcyto, as far as I currently know at the time of this recording. If there's any bugs as far as conflicting versions between these different packages, we'll have to navigate that accordingly. So, as far as planning, it's always good when you're working with code to kind of sketch out an idea of what you're trying to accomplish today, and then break it into smaller steps that you can then tackle sequentially. It's also worthwhile thinking in today's application, what would the different steps be if you were using commercial software and you were trying to extract out spectral signatures for use in unmixing, because a lot of those will parallel directly the different steps that we try to implement within R. So, since we're working with an R, we know we'll be working with FCS files that we have retrieved from the import repository. We'll need to load these into a gating set object similar to what we've been doing throughout the course. Likewise, because debris, doublets, dead cells, all will have different autofluorescence, and they're also very prone to non-specific staining or to stickiness in general, we will want to make sure that we implement some cleanup gates, probably using the flowgate package, just so we're isolating the cell or bead population that we are pretty confident will give us the best signature overall. And once those initial cleanup gates get implemented, we need to draw a gate on what we consider cells that are being positive for a given fluorophore. So ideally, those that are staining as bright or brighter in terms of MFI for that peak detector where most of the signal from the fluorophore is coming from. This will in turn dictate what we set as the x-axis on our one-dimensional histogram plots when we're doing these kind of drawings. So once this is done, and you have that positive gate for your probably positive cells, we will need to retrieve the experts matrix just for those cells that are contained within that gate. We'll need to do a summary measurement, generally in the form of either taking the median or the mean for each detector, at which point we can subtract out the background, and that gives us the values that just correspond to the fluorophore's contribution. At that point, what's typically done is we normalize the signature so that everything is values between 0 and 1, which allows us to contrast it with the other fluorophores. And then at that point, generally what we should do is visualize the signatures just to make sure that we actually did it correctly and that they don't look significantly off from what they should be. So if we do have access to some of those references that are published, it's often useful to compare what we get to what they have, and always knowing there will be a little bit of variation on a per instrument basis, but if it looks completely different, then there's probably something wrong with our code. And then, of course, this was all for just a single fluorophore, so if we're thinking of a regular spectral flow cytometry panel and we have 20, 30, 40, 60 colors, at that point that means, don't worry, we don't actually have to repeat all those same steps for each individual fluorophore. We're going to take advantage of other people's functions to make this part way less painful, especially for those medium and large panels, especially now that we're crossing into the 60-color spectral flow cytometry boundary. So, in terms of today, let's go ahead and start off with the setup. So, let's go ahead and load in our FCS files into our gating sets and get some of those cleanup gates implemented. So, fortunately for us, we've been doing this quite frequently over the last 5 weeks of the course, so we can just go ahead and repurpose the code that we have run previously and put them into this particular walkthrough. So as always, we need to attach our actual R packages that we'll need for today, and this can be done by using the library function to attach them to our local environment, which will make all the functions that are available within those packages utilizable for when we need them later. And for now, we're using a bunch of the Cytoverse packages as well as a bunch of the tidyverse packages in general. So at that point, we need to designate our file path to the folder that contains our FCS files. So if you're following the course project folder organization, that would be within week 12. It's going to be that data folder. Alternatively, if you're bringing in data from your external hard drive, you just need to point the file path to that location on your external hard drive. So that's going to be what we normally would do when we're creating a storage location through the use of the file path function. Additionally, we're going to be generating several intermediate objects throughout the course of today, and it's quite useful to have these in an individual folder so it's not cluttering up your working environment. So I will go ahead and designate an output location to a new folder I'm going to go ahead and create, which I'm going to call outputs, just to make sure that's where it ends up being placed.
So, with that file path now designated, let's go ahead and check to see what FCS files are currently present in that folder. So, when I'm checking for storage location, which was data for this particular week's work through, and I'm checking for FCS files, I can see I'm getting back around 68 FCS files for this downsampled data set. And just glancing at it by eye, I can see there's beats controls. I can see as I scroll down, we start getting to these cell controls. And if I scroll around a little bit, I will also find that it contains a few things that are likely unstained controls for the individual specimens. And at that point, where maybe you're interested in trying to break this apart, so instead of having everything in a single solid gating set and then trying to remember what is a bead and what is a cell, potentially we want to go into the file names and separate them out at this stage so that they're all in their respective gating sets. So if we look at those bead controls from the last page, we can see that all the bead controls start with ILT_00 as part of their file name, as well as they all include between parentheses the beads. Character strings within those names. Vice versa, for the cell and mixing controls, we're seeing that they all have ILT_01 in the file name, and between the parentheses, they have cells being present. So if we're trying to separate out these two, you could use these character strings to kind of be able to delineate out what is true and what is not. And vice versa, for those cell unstained controls, we find that they're being delineated by the use of the _unstained character string, so if we're trying to pull them out, we would use that likely in a structure detect object. So if we go back to the stringer package, we have been using structure detect, which basically, when it matches a particular character string, it will return as a value of true for that particular index. So at that point, we could combine it in with the square bracket notation that we've done to basically subset down a vector or a list, so that when these values come back as true, that match a particular character value that we have provided, these end up being provided to their own variable, to their own object, which we can use to load into a gating set. So what this would look like in practice for the beads is basically I have this original vector list containing all however many FCS files we have, and then running structure detect, I'm passing it that list, and I'm having it search for bead within the file names. At that point, it's only going to be returning to us things that did contain bead in the file name, and as you can see, we end up subsetting down this vector list to only be the bead controls for this particular gating set. Similarly, we can swap out the character value being searched for by structure detect, and we can end up isolating out just the cell controls. And likewise, we can have it search for the _unstained just to pull back the tree unstained samples for individual specimens. And just glancing at this one, we can see some of these are going to be controls, some of these are going to be PMA itemized and stimulated, so there may be some differences in autofluorescence depending which of these we're actually using. So now that we have separated out individual FCS files based on the type of a mixing control, let's go ahead and proceed to load them into their own respective gating sets. This will make our lives a little bit easier in the long run since we will only be working with one type of a mixing control per gating set when it comes time to actually iterating through. So how this would look, we're just repurposing code that we've seen in the past. We're using the flow workspaces packages, load cytoset from FCS function. We're creating a little first cytoset, and then we're wrapping it in a gating set through the gating set function so that we're able to work with it in R. And then we're repeating that process for both the cell controls, single colors, as well as the unstained cell samples that we have present in their respective vector list. So, if you recall back to previous weeks, you may remember that at this point in pre-processing, we are normally transforming our fluorescent detectors and our different parameters that are fluorescent. So, if our ultimate goal is to be able to go in and extract out the spectral flow cytometry signature that's present from these raw FCS files, you may be wondering if we actually need to transform. Given that when we transform, we're basically compressing the actual original values to fit a particular linear-like range, and all those changing of values are probably going to distort the overall signature. So this intuition is a good one, and it is indeed something that we are trying to avoid. However, between where we are currently with an assembled gating set and that point where we're extracting out the X-burst values to be able to get at those raw values we need to derive the signature, we still need to create a positive gate on the events that are as bright or brighter for the given fluorophorus peak detector. Since these fluorescent values tend to be very spread out when in terms of a by exponential scale, Doing this without transformation as far as in applying the gate in any reasonable manner and delineating it from things like antibody aggregates can be rather challenging. So at this point, in the context of our workflow for today, we're going to go ahead and transform first. Then we're going to go ahead and gate on those cells that we deem to be positive. And then we just have to remember at the time of creating the cytoset back and then extracting out the expers matrix, we need to provide the inverse.transform is equal to true argument so that those transform values get reverted back to the original raw values so that we don't end up distorting the overall signatures. So let's go ahead and actually transform our fluorescent parameters. So as you may remember from previously, we're taking the column names of our gating set. It gives us back basically the individual fluorophores plus the forward scatter, side scatter, and time. We don't want to include forward scatter, side scatter, and time in our actual transformations because those are more on the linear scale. So we're using structure detect to identify them, in which case these are going to come back as true when it's present in the column name. But through using that little exclamation point, we can flip it, so anytime something comes back as true, it gets excluded, and anytime something comes back as false, it gets retained. And then at that point, we end up with just the fluorophore detectors as far as the names that are going to be transformed. And then we can just use the float workspace code to apply the bi-exponential transformation. And this was the particular values that were being used for this particular data set, namely there was 5.62 positive decades, and there was a width basis of around negative 1,000. Obviously, your gating sets for your own data may look very different, and as we saw back in week 7, the easiest way to mess things up is applying the wrong transformation values in terms of being able to get good resolution. So this is one of those things you can play around with and see what's going to work and what's not going to work for yours and visualize it just to double check. But then we can go ahead and transform all 3 of our little gating sets just to make sure everything's set up properly for when we're drawing gates. Now, for this point, we can go ahead and implement our cleanup gates, and there are a couple methods by which we can implement them. So let's go with the manual method that we saw using the FlowGate package because it will allow us to open the Shiny app for now, which in turn will allow us to see the functionality of the new functions that were integrated within it in the last couple weeks. So, first off, the easiest way of assembling something is going to be through that gating table template for where I can create the gates iteratively all at once by reopening the Shiny app repeatedly. So what this is going to look like is similar to what we've seen in the past. For beads, I'm going to go ahead and create a scatter gate first, followed by a singlets gate. For the cell gates, I'll go ahead and create a singlets gate first, followed by the scatter, so they are a little flipped. But then at that point, all we need to do to actually apply this initial gate on the basis of a single specimen, but have the gates applied to all the specimens, is to use this gsapply gating strategy function. So, similar to what we've seen in the past, when we run this flow gate function, we're providing our gating set, and we're providing the actual gating table that's going to be used to draw the gates. And then when we run that line of code, what's going to happen is a Shiny app is going to launch, and then we're going to be able to select the option of draw with a polygon, and we can draw around where we think the scatter gate for these healthy looking beads is actually going to be. If we're happy with it, we can select done, and that gate will get created and applied to all the specimens in the gating set. If we mess something up, if we accidentally hit the rectangle and then we start drawing and realize we hit rectangle, you can go ahead and hit the reset function and then try again at redrawing the gate. But then ultimately you hit done to proceed to the next one, at which point, because we're running this one, it's going to pop in the next gate that gets created. So we're going to be drawing for singlets, and once again we can switch to polygon, we can draw our gate, and then we can select done. Now, with those initial gates now created and applied to our gating set, we really need to evaluate whether they were applied correctly to each individual specimen. So, back during week 8, when we first encountered FlowGate, the old version of the package was a one-size-fit-all. If something was off for one specimen, you would have to increase the size of the gate by redrawing it for everybody to be able to then apply it and actually capture it. But this was not always going to be cooperative, especially when you have a lot of different conditions, a lot of different donors, so it was a little bit clunky and it was kind of a pain in the neck to try to adjust things after the fact. Now, the ability to change a gate position within your gating set for an individual specimen was already something that was present within the Flow workspace package. So basically what I ended up doing was I took this initial function that we had, I ended up changing it a little bit to take advantage of this ability to reposition the gate on an individual specimen basis, but then I set up this new function, which is the gsapply gate check function, which rather than iterating through individual gates that get created, you just provide it the name of the gate in your gating set, and it will iterate through each individual specimen in that gating set, show you the gate as it was previously applied, and then allow you to redraw it on a per individual basis, and then save it on a per individual basis so that you can make the corrections. So basically, very similar to what we'd be doing in our regular workflow if we had been using commercial software. So what this looks like in practice, so we need to first go ahead and check the scatter gate, which was that first gate created for the beads. And as it's running, you'll see it pop in, kind of like similar view of what we've been seeing in the past. If the existing gate, which is shown in red, is good enough, you can go ahead and select Done, and it will move on to the next specimen. If, however, it's kind of off and you think you can draw a better gate, you can go ahead and select Polygon, draw that new gate, which is going to show up with the black lines, and then at that point you can select Done, and it will iterate to the next specimen. And here's another example where that initial gate that we drew based on the general application based on one specimen was clearly off a little bit for this bead control. This allows us to be able to adjust it and have it reflected correctly for that individual specimen going forward. Now, once you have gone ahead and iterated through all the specimens in your gating set in terms of scatter, you can then repeat that same process when it comes to those singlets. So we're just really swapping out the name of the gate, being checked iteratively, and then at that point we can see if the singlet gate is good, we can go ahead and select Done. If it's off a little bit and we want to make the adjustments, we can select the gate we're using, in this case Polygon, and then draw it, and then select Done. And here's one where it was majorly off when it comes to that original gate applied uniformly across the board, so we can make those adjustments in time as well. And with that, with relatively less pain than what it used to be to try to adjust these all via Flow Workspace on an individual basis, we are able to quickly iterate through all the different specimens, all the individual gates for each individual specimen, and make sure they're applied correctly. So then at that point, we really just need to repeat the same kind of process when it comes to our cell single colors. So at that point, remember, we're applying the initial template we wrote with the gsapply gating strategy, which is going to look like this. Obviously, we're working with our cell single color gating set, and we're applying the cell gating table. And then we're drawing our initial gates, giving a little bit extra room, just because we know it's going to be a little wobbly. Then we can go ahead and draw scatter. And remember, we're working for this particular walkthrough with the severely downsampled files, so everything's going to look zoomed in because there's no debris or other data to focus on for ggplot when it's zooming in on the plot. And then at that point, similar to what we did for beads, we can run the new gsapply gate check function and just iterate through all the individual combinations. So if you're checking the singlets gate, you can see this was one where it completely missed the actual correct location for the specimen, so we can go ahead and redraw our singlets gate for that one. Here's another one where it was off. You can go ahead and redraw it accordingly, and then at that point you can repeat for scatter and similar thing. There's a couple areas where they were clearly and obviously wrong. So at that point, you're quickly done with the cell single color controls as far as those cleanup gates, and you're good to proceed to the cell unstained. Fortunately for us, this is only 3 samples, so it's relatively quick. So once again, applying the initial gating strategy, drawing those initial gates, and then going through gsapply gate check just to make sure they're applied correctly for everybody. So you can see this one wasn't quite as stretched out as it needed to be for the singlets, and so on for scatter, was not quite grabbing what I had for the lower edge for this particular population. And with that, all the gates have been applied correctly to all our mixing controls. They have all been checked, so they're all ready to go. And we're going to have the cleanest population of cells or beads to work with when it comes to the cell signature extraction. Alright. So, with those cleanup gates implemented, let's go ahead and wrap up the setup process by adding in some additional metadata columns. This will end up making subsetting the gating set later on when we're working with the individual mixing controls significantly easier. So currently, if we check the metadata, which is via the pdata function for our gating set, we would only see a single column, namely the name column, which has the file name that we saw visualized in the file paths. So it would be, this is what you're going to see in terms of all the actual metadata. So as a file name itself, it's not particularly useful, especially because a lot of these have these extra digits at the end, which are the import repositories identifier. But there's also some quite useful information within this file name that would be better off extracting out of the file name and placing into its own columns. So we can see this is the fluor for APC R700. We can see it's the antigen is CD107A or LAMP1, and we can see that this single color was a bead type control, so each of these could be its own individual column. So, fortunately, there is a way using structure extract from the stringer package to go and extract particular patterns that are located between particular identifying characteristic objects and return them to a properly formatted column. Unfortunately for everybody, this relies on regular expressions, which tend to not be people's fortes, but fortunately for large language models, they do have swallowed the entirety of the internet, so they are able to regurgitate out the correct syntax that you would need to provide to structure extract to get at these relevant bits of information for your own particular file name. And then you can add these in as new columns through the use of the dplyr, packages, mutate, and case when functions, alongside the stringer functions that are used to kind of clean up some of those intermediate bits. Of course, we want to make sure that when it's actually being applied to our code, that the regular expression pattern we got back from an LLM is actually correct, and it's not just hallucinating garbage that leaves a bunch of random characters that we can't actually decipher. So what this looks like in practice, first off we need to grab our metadata. So using pdata function, we can grab it on our gating set. We get back a little data frame of the original metadata, which is just that initial column. We're then passing it in through the pipe to the mutate function, and this is where the LLM suggested code is happening. Basically, it's grabbing the raw information as far as structure extract. It's grabbing everything between basically the DR portion of the file name all the way towards the end. And then at that point, it's doing some cleanup on this raw intermediate to give us our antigen column, where it's getting rid of an additional bit of pieces. It's generating a fluorophore column, where it's getting rid of these additional bits and pieces. And generating a type column, which is all these additional bits and pieces. So as you can see, this is why I will give this task to an LLM. I don't want to have to remember what this hieroglyphic code is to get at a particular pattern for a file name that will often and not vary one data set to the next data set. And then at that point, just to make sure everything's a little standardized, I'll make sure I use the dplyr relocate function. I think I went a little too far. I went a little too far. Give me a second here. We were at metadata cleanup, so we're way back here somewhere. Metadata, beat single colors. And yeah, for these guys, we can then relocate fluorophore, antigen, and type, place them after the name column in that particular order, just to make sure they're going to work for us later on. And then, of course, we can save it as an intermediate, just in case we need to append it on later on. We have this intermediate metadata that we could then use. So what this ultimately looks like in terms of the initial cleanup, we need to see if it was hallucinated garbage or not. We can see that, yeah, this regex pattern we got from the LLM actually did a pretty good job. The bead unstained did not come back correct, which is why we have those two NAs. But for all the fluorophores, it looks like it grabbed the fluorophore pattern correctly. It ended up grabbing the antigen name correctly, and it grabbed the type of beads across the board correctly. So it did the vast majority of us and saved us all that effort when it came to writing these all out individually in a CSV file, which is always the not way to do things. So not horrid, it looks to be good. We can go ahead and use it and just modify it a couple changes that we have encountered. So one thing to consider, especially if you're using an instrument that is a shared resource facility instrument that has been around for a while, that didn't come with all the original fluorophore names preloaded, but instead has had users add them over time, is that not all the names as they are inputted into the instrument system are going to exactly match the names as they are provided by the manufacturer or as are present in a reference library. So at our core, this is typically because the original user who inputted them in either added or removed a hyphen, a space, they abbreviated Alexa Fluor to AF, some other variation of that. So we'll be using the Lucianaga package for signature comparisons, and it has some reference controls already present as part of its dataset. Not all of them, but some of them. So if we're trying to be able to take advantage of its functions, we need to make sure that the character name matches, so it's able to dig it out for its particular dataset. And basically the way it identifies a particular spectral instrument is through the use of the number of detectors value, and you can look up the information as far as like if you have a BD, if you have a Sony, if you have a Cytec Aurora, whatever variant of a spectral flow cytometry you are, what the number of detectors are. You can check this in the help file for the QC reference library function. So for our particular example, we're using a Cytec Aurora, a 5-laser system, which would be 64 detectors, so that number of detectors value being provided would be 64. So let's first off go ahead and grab our current fluorophore names from our intermediate metadata data frame, just so we know that what we have present. And then at that point, what we really want to do is grab the existing set of reference names, reference fluorophore names that are present for our particular instrument in the Lucianaga package, and compare the names for our current metadata against them, and anything that's left over that's not found in Lucianaga, have it returned to us as an environment so that we can decide, is it just because it's not in the reference library, or is it because there's a difference in the name convention as far as how it's written out. And we can do this via the base R setDiff function. So what this would look like is basically we're running instrument references, which is an internal function. You can see it has these 3 little colons. It's not something that you would encounter normally on a day-to-day basis, but we're setting our number of detectors equal to 64, which is what we saw was the correct value for our Cytec Aurora. And then we're iterating it in, we're passing it through the pipe to the pull function. We're just grabbing the fluorophore column, and we're only keeping the unique entries, which just gives us the available references that we have in the Lucianaga package for that given fluorophore. And then we're using a setDiff function from base R to basically compare all the individual individual names in our control names against this reference set, and give us back anything that doesn't match. So in this case, for the ones that we have currently in metadata, NA, because that was the bead unstained sample, is not present in the reference library, which is good. But then we can also see pVial 770 and pDazzle 594 are not being recognized, which is a little odd considering they're more of the older generation of fluorophores, so they should be present considering a bunch of the other ones are. So, at this point, it's likely there's a little bit of difference in terms of the naming syntax for these individual fluorophores because they're PE tandem dyes, so we should kind of figure out how is it actually stored within the reference library. So we can do this via the QC reference library function from Lucianaga. Basically, we're able to provide it the character string that will be contained within the fluorophore name, and it will return anything that has a match for that within the reference libraries that it has available. So, for example, for checking for pVial 770, we can go ahead and use 770 as our character value. We're passing it to QC reference library function. The argument is fluor name contains. This is where we provide the value that's being searched for. It also has the ability to return us the actual plots, so we can see what the difference in the individual fluorophores looks like. So I'll go ahead and set that as true. And as it's a 5-laser aurora, I'll set number of detectors to 64. And I'm saving this to this intermediate object or variable, which we'll know as vial, so that we're able to work with it accordingly. So once we're at vial, we can see that within the available references for our individual instrument, there's pVial 770, APC Vial 770, and CF 770 across the board. So for this one, what looks to be happening is this is going to be one of those situations where it's likely this extra space is the main difference that we're seeing in terms of our original metadata that we grabbed from the file name itself versus what's actually present in the reference library system. Additionally, since we are getting back that return ggplot2 object to view the signatures, we can use one of my favorite packages, Plotly, specifically its ggplotly function, to change what is currently a rather static ggplot2 view of the signatures to an interactive one that we're actually able to mess around with and see where the different peak detectors are located at. So the way this would work is that intermediate object we got back from QC_reference library was a list both containing the previous layout view of these similar matches, but then also the second object in the list is the actual signature plot. So what we're doing is basically getting at that second object in the list through the use of these 2 square brackets next to vial. We're now having just the ggplot object. We're wrapping it with the ggplotly function. At this point, we get back a interactive object, which is a little compressed right now in the slide view, but you can see I can actually see what is the p-vial signature. So I can see this is the YG9 as its peak detector, the blue 13, the violet 15, and then I can contrast it, for example, to the CF770 by clicking in, and I can see the differences mainly being over here on the violet 16. And then likewise, you can save this as a plot, you can zoom in, you can zoom out, you can pan, you can do a bunch of other variants as far as things go with these plots, so they're quite fun to play around with. So, at this point, it looks like the issue with the naming convention is simply we need to add a space between vial and 770 for this particular fluorophore. We can then follow up with the dazzle fluorophore to see if there's any other ones that we might be encountering. So in this case, we're just swapping out fluor name contains from 770 to dazzle, keeping all those arguments the same. And then as we proceed, we can see there's only one fluorophore in Lucianagas for this instrument setting that has the word dazzle in it, so it's dazzle 594. Right off the bat, it looks like, yeah, there's an extra space there. We can plot and visualize it across the board if we really want to. And as we can see, let me go ahead and zoom out a little bit. We can see that it's a YG tree detector, it's a B6 detector, so on and so forth. So all we need to do is add missing spaces in to our existing metadata names, at which point it's going to be able to flawlessly cross-match to the reference library, and you won't have to worry across the board about not being able to see it when it truly actually is there. So, and there's also, of course, the consideration of what happens when you're searching for a fluorophore that just doesn't happen to be in Lucianaga yet. That's a situation you can see, for example, if you look at the BDS8 instrument, which is going to be 78 detectors. If you search for real red in it, you're going to get back a return value that looks something like this. This is what happens when a fluorophore is just not yet in the system, so you're not able to search for it. Alright, let's go ahead and exit this rabbit hole in terms of naming syntax, and let's just go ahead and quickly add the space into the existing metadata. So the simplest way of doing this without having to write it out as a CSV, change it by hand, read it back in, instead to do it entirely programmatically inside R, is through the dplyr package's use of the mutate and the case when functions. So what this looks like in actual practice is we have our data frame, we're passing it through the pipe through the mutate function, and then we're currently working on our already existing column fluorophore, and basically we're using the case when statement so that when the value in the fluorophore column is equal to, denoted by these two equal signs, p vial 770 without the space, it's going to be converted into everything that's after the little tilde, so p vial space 770 is what it's going to get converted over into. Similarly, if within the fluorophore column, it recognizes the value that's equal to p dazzle 594 without the space, it's going to get converted to this part after the tilde, so p dazzle with the space 594. And then because we don't want all the other values in the column to get converted to nulls or not applicables, we'll leave this set to true tilde fluorophore so that anything that doesn't match these two particular original names will be left with what the original name they had without generating a bunch of nulls. And we can also use the same application to target our bead unstained sample, which is what gave us back those two Na values for both fluorophore and antigen, because the stringer structure extract pattern that we provided for the regex didn't quite account for what the file name was structured as. So we can go ahead and rename these accordingly. So for antigen, we can see if it's going to find a situation for the actual file name itself, which is going to be the bead unstained, as far as the structure detect, recognizing it in the name. We can just have it set the antigen to not applicable character so that it stays consistent across the board. And then we can set fluorophore when it recognizes bead unstained in the file name column. It can go ahead and rename it to bead unstained for that fluorophore column accordingly. So we can go ahead and quickly check this. So we can see bead unstained is going to be our first row here. So if we scroll down, because not everything's in the same view, we can see fluorophore has been renamed to bead unstained. We can see antigen is left as an Na value. We can see all the other fluorophores that are not p-vial 770 and are not p-dazzle are still retained their original information. But as we scroll down and we run into p-vial 770 and p-dazzle, we can see they have been renamed to include the space. So now they're matching things accordingly across the board. So at this point, everything looks good. We can go ahead and swap in the metadata for our bead getting set. And basically, we're just grabbing our now updated metadata and overwriting the existing one through the use of this assignment arrow, pointing back at the p data of our particular getting set. And then at that point, if we call it again, we can see that everything has been updated. We have these additional columns that we can then use to subset down later on if we're only interested in a particular set of fluorophores. So with that done, all we would really need to do for this walkthrough would be repeat those same processes as far as metadata cleanup for our cell single colors, which are going to be very similar in their name syntax. So as you can see, it's the same set of code we got back from the LLM. Obviously, it's going to be looking for cells instead of looking for beads. And then ultimately, we are doing all those modifications. We can store it intermediate. And then when we are checking, we can see it comes back pretty clean across the board. Still has the need to add those spaces, so we can go ahead and add in those spaces should it use the mutate in the case when function. And since there's no bead unstained in this particular gating set, we can just skip that line of code and go directly to appending it into the existing pdata. And then at that point, our cell single color controls are also similarly updated in terms of their metadata. And because there's only 3 specimens in our unstained, we could do the same kind of steps to be able to delineate what the condition of the unstained is, what the donor was, but because there's relatively a few of these, we'll just consider this optional for today and skip it for today's walkthrough. So at this point, we have put a lot of effort into getting our gating sets created, transformations applied, cleanup gates created, and metadata updated. So we're at a really good point to go ahead and pause this workflow and save these gating sets as intermediate GS folders so that we can reload them back in the future, either later today, tomorrow, next week, next month, whatever the case may be, and you can be back exactly at the save point where you had left it at. So the way we are doing this, if you remember back to week 5, for the gating set object, it's going to be the save.gs function from Flow Workspace. We're basically providing a file path to a new folder that we're going to create, which is going to be beads single colors underscore gs.gs. The .gs being denoting it is a gating set intermediate folder. We're going to go ahead and save it there. And then in terms of loading it back in later, we'll use the equivalent load.gs, pointing at that exact same file path. And we can then save it to the exact same gating set name. So it's basically save it and return it back relatively ease across the board. And at that point, we can repeat the process for both our cell single color gating set as well as our cell unstained gating set, just so all that hard work we've put in for these last 45 minutes of the walkthrough is not lost when it comes to later on with a bunch of the other edits we need to make. And with that, we are finally through the setup process, and we can actually start tackling how to extract out the fluorescent signatures. So, let's start off by working with our cell single color gating set and our cell unstained gating set. So, if we had just saved our object and we had come back an hour later, 2 hours later, a day later after we had reloaded positron, we could load back into this exact same point using the load.gs function. And this is what it looks like reloading in the intermediate GS folder we had saved it to for the cell single colors, and same code rerun to get in our cell unstained gating set to make sure it's available in our local environment. And we can double check to make sure that all those gates we had hard fought to create and check are still there. We can see that yes, they are. And then at that point, let's, for this particular walkthrough, just focus in on APC Fire 810 fluorophore for reasons that will become more obvious the later we go today. So to actually separate this one out from the larger data set and subset it into its own gating set, we're going to take advantage of both the subset function, which will work on bioconductor S4 objects, as well as the use of filter to basically identify within the metadata for the column fluorophore, something that matches the APC Fire 810 expected value. So what this looks like in practice is we're passing to the subset function our gating set. We're setting this little conditional filter argument of when fluorophore is double equal to APC Fire 810. That's what's going to be used to actually subset down. And then realize view equals true is basically you've got to make sure there's another copy of this beyond the original one so that it can work independently from each other. And we end up with a new gating set, APC Fire 810, that only has the APC Fire present. Alright, now that we have a small gating set just dedicated to APC Fire 810, we still need to create we need to still gate on the positive events, which we can do through a span gate to isolate out cells that are positive for our particular fluorophore. At that point, as we're going to be creating a span gate, which is typically done for one-dimensional a one-dimensional histogram, we're going to need to figure out what the peak detector for our given fluorophore is so that we can designate that as our x-axis. So if you're very experienced for spectral flow cytometry or in context of your particular panel, you may already know what the peak detector will be for your particular instrument. However, if you're working with a data set that you got from import or from flow repository, you have a couple options. You can check the instrument manufacturer's websites, or you can use something more general like Fluorofinder. But also, because Luciarnica does have some of these references available on the instrument, you could also go and take advantage of that and check quickly within R. So what this is going to look like is basically we're checking QC reference library for our particular fluorophore of interest. In this case, we're giving it the full name for APC Fire 810. And we're just going to head and iterate into the ggplotly so we can see this interactive view. And then at that point, all we need to do to be able to figure out that peak detector is hover on top of the peak, and we can see it's going to be the R8 detector for this particular fluorophore. So that's what we should set for our x-axis. However, especially for a lot of different instrument manufacturers, you may also have variants of the detector, like area, height, and width. And just because I or my instrument have it set to area doesn't mean that your instrument is going to be the same. So we should double check to see what actually the little designation is going to be for this individual detector. So if I check column names of our gating set, we can see these are our column names. And even though scatter and time and forward scatter do have the width, height, and area variants, we can see all the individual detectors as far as the fluorescent ones have the little -A denoting area present. This will be different on different instruments, so when I tried to run this code on a Sony instrument relatively recently, it ended up coming back with tree results for area, height, and width because all of them were included in a single go. So this is one of those areas you need to troubleshoot depending on your own instrument settings. Okay, so we need to set R8-A as our detector value when we go in and create a new gate. So we can create a new individual gate via flow gate through the GSGate interactive function. So what this is going to look like, borrowing that code back from week 8, is basically we're providing it our gating set. Filter ID is going to be the name of the new gate. I'm going to go ahead and call it APC Fire 810. I'm going to draw this on sample equals 1. We only currently have a single sample in our gating set, so that's fairly easy. Remember though, if you're working on a full gating set, you want to actually denote the correct sample, or else you're going to be drawing the positive cells based off of the R8 detector, but if your single color fluorophore is BUV395, you won't have any signal on that detector. So those are the things to watch out for. And then for DIMMs, you can go ahead and specify within the list format, we want it drawn on just the R8A detector, which will draw it into a one-dimensional histogram. And then subset basically says, under which existing gate do I want to create this new gate, so it will be under the scatter parameter. And then at that point, we can just select the span option, and we can go ahead and draw our gate. So generally, initially, I'll just go ahead and start from as bright or brighter. So I'm just going to start from the middle of the peak and go all the way over. Once I'm happy with this, I'll just go ahead and select done and go ahead and create the gate. At which point you can see it's now placed underneath the scatter. However, if you do decide that that is too liberal, you need to make it just even more narrower at the top of the peak, you can use the GSGate interactive adjust function to go back in and edit it. So once again, you're providing your gating set, you're providing the actual gate that you want to edit, and you're just going to go ahead and do a couple additional arguments here. And then at that point, if you say, okay, this was the original gate, you can see it denoted in red. If you actually wanted to go ahead and make it a little bit more narrow, you could use span, draw the new span corresponding to everything within this region of the curve, and that will be included across the board. And then select done, just to make sure it's saved. At this point, we should go ahead and draw an internal negative gate so that we can have it for a couple examples. So we should go ahead and set it as its own span gate. So in this case, what we're going to do is, once again, we're drawing a new gate, so we're going to call it a new one. So it's going to be filter ID is equal to internal negative. We're going to keep this on the R8A detector, just so we're able to make sure we're not accidentally grabbing fluorophore positive cells. And it's still going to be underneath the subset scatter gate. And this is the kind of gate I ended up drawing for our internal negative. For those of you who prefer to use an external unstained, we will do that in a couple minutes for the next step. And then at that point, because we have created additional gates and we may want to come back and revisit these individually, let's go ahead and save APC Fire 810 to its own intermediate GS folder so that we retain the ability to come back in and go back out without needing to redraw the internal negative and the APC Fire 810 positive gate each and every time. And this is ultimately what our little gating set is now looking like at this point. Alright, we now have our span gates created. We are at the point we can go in and extract out the X-verse matrices. So to be able to do this, we first need to retrieve from our gating set a cytoset that corresponds to just the gated cells that are present within this gate, which is what we're going to be doing via the gspop get data function, which is something we encountered back in week 10 when we're doing the downsampling and the concatenation. So the main thing, as we mentioned at the beginning of today, is we need to remember to specify inverse.transform is equal to true, so that we reverse the transformation steps so that we're actually working with just the raw values. And then at that point, we can then use the X-verse helper function to go in and grab the actual X-verse matrices, so that we can then look at the actual raw data in terms of a matrix. But it's often useful to go ahead and convert that over into a data frame so that we can use some of the plier package functions when we're doing some of the selection of the various individual columns. So what this looks like in practice is we're running gspop get data on our gating set for this particular gate, APC Fire 810. We're remembering to set inverse.transform is equal to true. And then at that point, once we have our cytoset, we can break in from the list view to just the cytoset itself through the use of those square brackets. And then we can directly grab the X-verse from there. We can save that as the matrix object, which we can pass the data frame function and set this check.names argument to false so it doesn't try to convert our column names from uv1-a to uv1.a or some other variation of that. And as you can see, we do have our raw values back. But at this point, I have been burned in the past because I thought I applied a transformation reversal, but I actually didn't. So let's just go ahead and look at a summary view just to make sure that the values we're getting back per individual detector actually look like raw values and not like the bi-exponentially transformed values that will be like between 0 and 2000 across the board for everybody. So just right off the bat, as I start to check, I can start to see there's negative values. For the positive data, UV1 goes up to like 1700 as far as the value. If I scroll down to where R8 is, I can see this lowest value is around 26 something and it goes to 137,000 something. So this seems to be more in terms of ranges I would expect for raw values, and most of the signal is being seen on R8A, so it's likely that the transform reversal worked correctly. So far so good. We can then repeat the same step for our internal negative gate as well, just so we have that data available so we can use it when it comes to the background subtraction. Exactly same thing, we're just specifying a different gate. We're saving it to slightly different named object variables in our environment, so we're not overwriting the positive data by accident. And at that point, we're set to go. And once again, quick summary, we can see that the unstained across the board is much lower down across the board for everybody. And if I scroll down far enough for R8, you can see it's nowhere near as bright for the max value. So yeah, we did grab just the negative data. We didn't accidentally grab the root gate, which included debris, doublets, and positive staining cells. Yeah. Alright. So, at this point, we have a lot of the elements we need for values to extract our fluorescent signature, but we still have a few extra detector parameters that are not actually fluorescent detectors. Instead, what we have is the forward scatter, side scatter, and time columns, as well as their area, height, and width variance. So we need to remove those from our data frame for both the positive data and the negative data before we move forward. So one way that we can do this is basically we can repurpose that code we've used in the past when we're trying to specify what column names will be transformed. We can instead have it what column names are going to be retained in the data frame when we're actually going to subset. So what this looks like is, once again, we're grabbing the original names, and then within the square brackets on our data frame, basically we're running structure detect, checking within the individual column names for anything that contains forward scatter, side scatter, or time. If it does detect them in the column name, it will come back as true, but then the exclamation sign will flip it, so it will be a value of false. And when there's a false value between those square brackets, it won't actually be retained, it will be removed. And that way we can actually exclude out forward scatter, side scatter, and time, which is what ends up happening here for this particular data frame. And then at that point, you would just need to repeat it for the negative to also similarly get rid of the forward scatter, side scatter, and time columns. So next up, for each individual detector, for all the cells that have their values there, we need to take some kind of summary middle measurement. Typically, I see this done with median, but I've also seen mean or geomean used in the past. So you can try around with what you want to do for these initial raw signal values. So ultimately what we want to do is on a per column basis, we want to summarize what the median measurement is and then save that as a new value for a new row. What we can use is the dplyr package's summarize all function to be able to get at this situation. So what this looks like in practice is we take our data frame, we pass it through the pipe to summarize all, and then we're just specifying which function is being used. So this is the median from base R. Alternatively, you could specify mean. And it finds the median per individual detector, and it returns to us that value. So at this point, we have a pre-processed signature. And we can then repeat the same process for our negative signature, and it's going to return to us the median of each individual detector for all the cells that were contained within our gate of interest. So at that point, we're now left with a single row with the median values for each individual detector. This is a pre-processed signature. It will still contain background autofluorescence. So we should go ahead and try to see if we can visualize this pre-processed signature, even though it still has some autofluorescence, just to make sure we're able to get the ggplot code working properly for it. So what we could also end up doing is take advantage of the Luciernaga package, which has that visualize signature wrapper, to be able to use that when it comes to visualizing the signatures. This particular function does require there be one character column name called fluorophore, designating what the name of the signature is, in case you're going to put it into a Plotly interactive plot. However, you're also free to take that original function from Luciernaga, modify it, and remove this requirement if you want your particular lines of code to work in a separate way. So, if you want to check quickly to see what this raw signature looks like for APC Fire 810 before we do background subtraction, we're just going to add in this extra little bit of information that's needed for visualize signature, creating a new column through the use of mutate, name of fluorophore, specifying the value for this particular signature as APC Fire 810, relocating fluorophore before all the actual numeric values, so placing it in the first column position, and then we're passing that data frame to visualize signatures. We're saying look at the column name of fluorophore. We're going to keep the normalized option set to false for now, just so we're seeing those raw signatures. And at that point, we can return a plot, which we pass into Plotly. And if I zoom out so that you can view it in terms of the screen, we can see this is the raw value that we just extracted from our single color control. So we can see the R8 detector is currently at 38,225 in terms of its median value. R1 is showing up at 16,804. YG4 is 9,418, and then Violet 7, which typically is autofluorescence, is showing up as 7,568. So this is a pre-processed signature. We haven't subtracted out background. Hopefully when we subtract out our negative background, a bunch of this little extra bit of noise will be eliminated, leaving us with just the actual fluorophore contribution to the signature. So that's the same description for the last sentence. It's additionally worth remembering that cells may vary in terms of the different levels of marker or molecular expression, which will correspond to differences in brightness signal being recorded. So ultimately, just because we're viewing this right now as a raw brightness doesn't mean it's going to be necessarily what we want to see for the normalized signature when everything gets scaled to 0 and 1. So let's go ahead and repeat the same process for our internal unstained so that we have a good general idea of what we expect for the autofluorescence signature for this particular gated region. So same thing, we're adding the little bit of additional columns needed to run visualize signatures, and then at that point we're going to go ahead and run it, get our plot, and then once we're at our plot we can go ahead and check it out. Let me go minimize. And we can see for our current autofluorescence running off of that internal unstained, there's a peak at Violet 7, there's a UV7 peak as well, a little bit of a blue tree peak, and then some kind of little rounded areas right around the red and the yellow-green detectors as well. Alright, so that's what our autofluorescence looks like. If we were going back and checking on that y-axis, what we can end up seeing is these values are substantially dimmer compared to what we see for the fluorophore, where everything is like several logs brighter across the board. So that's one thing to remember as we're doing signature comparisons. So far we've just been looking at this pre-processed signature. We have not yet subtracted out the background. But there is one useful function in Luciernaga that's worth mentioning at this point, which is the QC what's this function, which will compare whatever signature that you provide to it to the reference library signatures to try to make an accurate guess of like what your fluorophore may be. So this is quite useful in terms of like there's this random tube that nobody knows what it is, but you got a signature, but you don't know what it originally was. You can pass that signature in to see what's this to be able to get that likely candidates out. But then we can also see with the autofluorescence incorporation, what does this APC Fire A10 actually look like compared to the other fluorophores? So basically, we're passing in our existing data for the positive plot data. We're setting it as APC Fire 810 as the name that's being searched for within the column name fluorophore. We're setting our return plots argument to true so we can visualize them, and I only want to see the top 5 hits in terms of similarity. So at that point, we get back these returns, and we can see, we'll talk about cosine values or similarity values next week, but for the time being, we can see that APC Fire 810, which is what actually this fluorophore is, when it has the autofluorescence background incorporated, it's only 0.8 similar to the reference signature. So this is one of those areas where if we do a rough cutoff of 0.98, we're going to expect to see mixing issues if we use this signature in its current exact state. And let's go ahead and check the return plots as equal to true argument just to be able to visualize this in a more direct comparison way. So our actual signal we have right now for our APC Fire 810 looks like this when we normalize it. The actual reference library, as you can see, is much cleaner across the board. We don't have whatever's happening here on R1 or YG4, and we don't have what's likely autofluorescence for violet 7, for UV7, and for the little bit of blue tree here. Alright, so at this point we can go ahead and subtract out background subtraction. So you may be thinking this is going to be complicated, there's going to be a lot of moving pieces when it comes to subtracting each individual rows, columns across the board, but it turns out both of our data frames are the exact same dimensions, and they are constituting the exact same numeric columns. So the only thing we need to do actually to subtract one from the other is add a minus sign between them. So it's basically literally a little positive signature matrix minus our negative signature matrix gives us back the subtracted background values across the board. So this is just the fluorophore contribution in terms of the values. At that point, we can repeat the process and be able to use the visualize signatures function just to be able to see what this looks like. We can also use the plier as far as the bind rows function to combine both the pre-process to the background subtracted signature just to see what this looks like in the context of our actual single color that we're working with today. So we can go ahead and do this little bit of cleanup gate both for the positives, the post-background subtraction, as well as the pre-background subtraction, bind them together into the same data frame, pass them to the visualize signature function, at which point we can see for our particular gating set, this guy here is going to be the pre-background subtraction, and this guy here is the post-background subtraction. So when we subtracted out our background, we lost a little bit of the signal for the UV7, the violet 7, and the B tree detectors, but there is still something quirky as far as comparison to the reference signature in terms of the R1 and the YG4 detectors. So let's go ahead and pass this post-process one to QC what's this to see how more similar it is to our reference signature. So when we pass this new one in, we can end up seeing that, yes, it's a little bit more similar to APC Fire now that A10, as far as the autofluorescence background has been subtracted, but it's still quite different from what we see for the reference control. Now, whether this is just an instrument difference from my instrument versus whoever acquired the references instrument, or if it's something else going on, it's something we'll touch on a little bit later today. But it's something to keep in mind as we go forward. And this is the post one as well. So yeah, same view, same plot across the board. Alright, so at this point we have extracted our underlying data, we have summarized the data across the various fluorescent detectors, and subtracted out the background signal. The only thing that has remaining to do is we need to normalize our particular signature values, basically bringing those values to be anywhere from 0 to 1. So the Lucianaga plotting functions we've been using have been handling this in the background, but it's useful to see how this is actually implemented in case you want to tinker on your own. So the way this is going to basically happen is we're going to iterate across each of the columns using the base R's do call function. It's basically going to be able to, if you pass it a function, in this case the pmax function, identify what value across all those columns was actually the max value, which is going to then save to an intermediate argument. And then at that point, in terms of actually going in and normalizing it, we just need to divide the actual existing value for each column divided by that determined max value across all of the detectors to be able to have everything scaled from 0 to 1. So what this looks like in practice, we can run do call, and then we're running pmax as a function, and we're having it check just the fluorophore as far as the different columns being checked. At that point, we can identify what the peak value is, which is likely to be the R8 one for this particular fluorophore. If we were running this on the unstained, it would likely come up with the violet 7 as the peak value. And then at that point, when it comes to normalizing or scaling, it's just dividing everybody by it. So as you can see, it's very similar. Just the fluorophore divided by the identified peak value. This becomes the normalized value, and just for a little bit of simplicity's sake, I'm going to go ahead and round it to a significant digit. So you can see peak value now is 1 for the R8 detector, it's 0 at UV1, and it's variant across the board depending on where the signature values are being picked up by our individual detectors. So why would we want to normalize in the first place? Can't we just work with the raw signatures? Well, we can, but if we plotted both our unstained and our APC Fire A10 raw signatures right now in a plot, this is what we end up getting. So if I go ahead and zoom out, you can see APC Fire A10s are very clear and obvious. They're way up here, they're very, very bright, but you can see the very peak of the autofluorescence right now for violet 7 is down here. So if I'm actually only looking at the background, it's very much not taking up much of the same space across the board. So ultimately, what we really want to do when we're comparing fluorophores is we want to be able to contrast how each individual fluorophore is returning photons across the entire spectrum, so that we can see how different they are to each other. We don't want it to just be drowned out by one of these fluorophores is way more efficient at giving back photons than the other, or it's on an antigen that's more abundant accordingly. So these are the kind of caveats that come into play. So ultimately what we're trying to do when we normalize is make it much easier to do the comparisons across the board. So as you can see, once we end up normalizing, we can see this is our APC Fire A10 signature versus this is what we would expect to see for our autofluorescence across the board. So it's much easier to compare. It's like, oh, autofluorescences are going to be giving a signal in the violets and the ultraviolets and in the blue for this particular instrument, versus this APC Fire A10 is going to be primarily within the red and the yellow-green laser. Alright, so with that, at the simplest level, we have seen how to extract and visualize the normalized fluorescence signatures for our APC Fire A10 and an unstained autofluorescence signature. So congratulations, you have broken through what's the first layer of what is very much a confusing black box when it comes to spectral flow cytometry for much of the community. Hopefully at this point you see how these different steps going from you gated on the cells to how you gated on those cells ends up being the actual signature in place that you will end up using for unmixing in a couple weeks. So I know a few of you are definitely reminding me on the screen that this is using an internal unstained, and not using an internal unstained is not always advisable. This is namely because depending on your fluorophore, you can have a lot of non-specific staining that gets added to those negative cells. So then when you're actually trying to subtract out the background, you end up subtracting out as well a little bit of the fluorophore. So for completionist sake, let's go ahead and do the same walk through little bits as far as the subtraction, but instead use an external unstained that has not been stained at any point with APC Fire A10. So this is where we have to remember for this particular gating set, we are working with the APC Fire A10 CD38. We need to identify if this was done using cord blood mononuclear cells or CBMCs, or if it was PBMCs that were actually used to create the single color control. This is, of course, going to be easier if it's your own experiment. If you're relying on somebody else's data set, it's going to be a little bit of pain, especially if they didn't keep the notes that they needed to. But for SDY3080, you can check the metadata, or you can check the lab notebook, and you can be able to identify out this bit of information. So for CD38, APC Fire A10, turns out it was run with cord blood in the control condition. So from our cell unstained gating set that we have, we just need to identify infant 52 for use of the external background subtraction. So let's go ahead and reload it back in from its intermediate.gs folder. and once it's active in our environment, we can check the P data. We can see infant 52 is the very first on in terms of the index, so we can then use that when in terms of being able to actually extract out the data. And in this case, because we're grabbing just a unstained control, we're not really focusing in on like a peak detector. We just want the general signal across the board. So it's perfectly fine when we're going to gspop extract for the data, just to use the scatter gate in this case. So in this case, we're running gspop get data. We're setting it for the first specimen in the unstained gating set, which is being done by the single square brackets 1 to grab infant 52. We're setting the gate being retrieved for as scatter, and then the code is very similar as far as extraction of the expers matrix, changing it to a data frame. And then at that point, we can go ahead and remove the forward scatter, the side scatter, and the time columns. We can get our summarized measurement in terms of the median for each of those detectors. We can reformat it to make it a little bit easier to work with visualized signature. And at that point, we can also combine it in with our already previously retrieved internal negative signature, just to be able to see how they differ if we had used internal unstained versus if we had to use the external unstained. So if we're comparing our two unstains, we can see in terms of just raw brightness that background, which would have been the internal, is a little bit brighter overall compared to this external. So in terms of that peak detector, the external is around 6,000, the internal unstained is around 7,200. So there's a little bit of difference when it comes to the brightness of these two. However, if we go ahead and normalize it and then check the scale, which is what's oftentimes very important to do, we can see as we zoom out that the signature looks pretty indistinguishable from both the internal and the external for both of the three main peaks, but that the internal does have a little bit extra contribution for these areas in terms of the R2 and the YG4 areas where there's a little bit of what's likely nonspecific staining going on. Now, of course, whether this little bit of nonspecific staining will actually impact our overall APC Fire 810 signature when it gets subtracted out is something that we need to go ahead and validate. So once again, we can just subtract from a positive signature the different backgrounds. So the internal negative signature versus a separate one, extracting out the external negative signature, going ahead and doing the polishing up so that we can visualize it. And then at that point, if we end up plotting the two variants of APC Fire 810, depending on what background we used, we can see it's very, very similar across the board when it comes to the actual components of the R8 detector, the R1 and the YG4. There is a little bit extra signal right now there when we use the external. This is on the V7 detector, which is likely due to that little bit of difference in the brightness when between the external and the internal unstained. So always something to be a little bit cautious about. How you draw these gates can impact what we end up seeing. And if we check the normalized signature to actually see the between 0 and 1 values, we can see a similar story. It's relatively minor by appearance. We'll actually evaluate how to compare signatures with each other next time. So, for this particular antigen-fluorophore combination, the overall signature didn't change dramatically depending on whether you're using the internal or the external autofluorescence for background subtraction, outside of some differences in the autofluorescence peaks detectors for V8 and V3, due likely to differences due to the external unstained being less bright compared to the internal unstained. The differences that we did observe between the unstaineds likely arose from nonspecific staining in the red detectors, but ultimately these didn't seem to dramatically shift anything when they were extracted out from the overall fluorescence signature. This is likely due to the actual positive signal that's present on the R8 detector is just substantially larger than these little bit of differences in the MFI of our autofluorescent detector, so basically they are negligible when it comes time at subtraction. And as with everything in flow, this is only applicable so far for this particular fluorophore antigen combination on this particular specimen, and this pattern has no guarantees to hold up for other fluorophores or even the same fluorophore on a different experimental day, but is a good illustration of the things to consider and keep in mind when you're carrying out the process of characterizing a fluorescent signature for its use in an unmixing control. So, now that we have some general experience with the basic mechanics of extracting out a fluorescent signature, either using an internal or an external background, let's do one of my time-honored traditions of going down a rabbit hole. So back when I was first learning how to unmix in late 2021, I was always curious, like when I'm drawing a gate on the positive peak, what would happen if I had shifted the entire gated region 1 or 2 millimeters to the left and right? Would that have affected the signature, and in turn, would it have affected my unmixing? So I could have done that myself, but it would have been rather tedious to do in Spectral as far as like I would have to just re-unmix as a separate experiment, compare them by hand to see if there's anything dramatically different when I shifted the signature. So it's not an easy task to be able to do using commercial software. Within our existing code base, we could implement something very similar using FlowGate just by modifying the gate around a couple of times. It's going to be a little bit easier to do as far as like getting out to the final view of the signature, but it's still not necessarily efficient when it comes to iterating through the different approaches. However, we can get a very functionally similar approach if our main question is a difference in the area of the positive gate going to retrieve different signatures? By basically, once we're at that extracting out the X-verse matrix phase, align everything in terms of the peak detector from values that are the smallest to greatest, and then at that point, basically apply bins, basically cutting every 10%, so 0 to 10, 10 to 20, 20 to 30, etc., and then for cells that fall within these bins, generate the normalized signature from each, just so we can see what the impact on the signature would have been if we had included a greater portion or a smaller portion of the positive signal. So this is what this would look like in practice. So if a normal sequence of events we would gated as bright or brighter and place it right here in the middle, what would the difference have been if we had just grabbed the brightest 10% of the cells or the dimmest 10% of the cells? Are we going to see a difference in the signature? So there are a lot of moving pieces when it comes to implementing it. So if you're curious about what these moving pieces are, if you open the Lucianaga packages GitHub page, this is going to be under Lucianaga linear slices function with all the little bit of background information. However, this has a lot of moving parts as far as like different arguments that you can provide. So it's not quite good to introduce this one at this point of today's walkthrough. It would be easier if we were able to provide a wrapper function that does a lot of those decision makings for you, just to allow for a cursory glance and allow the fine-tuning with the actual function to be done later on as you get your own workflows established. So this wrapper in this context for the course is going to be the Lucianaga integration function wrapper, which basically will generate a bunch of those Lucianaga plots and retrieve a bunch of the Lucianaga data and just return it as a named list that you can then isolate out the particular plot of interest based on that gate you had drawn and get those same kind of bits of information. So to actually take advantage of this wrapper, there's a little bit of additional information that needs to be provided to basically a data frame we're extracting from the P data. Namely, it needs to have a detector value and a negative column as well. So we're going to need to do a little bit of data tidying with dplyr for our P data before we are able to use it. Additionally, it does require that the name of your gate matches the name of your fluorophore. We can do this retroactively through Flow Workspace by just using the gspopsetName function, which allows us to rename an existing gate. And we can use that to set the correct matching syntax. And then at that point, we can just go ahead and make sure we save everything and to its own little variable that we can then check that name list for later. So in practice, we're grabbing our metadata. We are relocating again fluorophore, antigen, and type, so they're in correct order. And we're going to use mutate to create a new detector. In this case, this only has R8A, so we can set that as the detector value. And we're just going to leave negative blank, so it uses the internal negative in this case. And then at that point, we just need to rename our gate for APC Fire 810 to be correctly matching the syntax of the fluorophore name. So it's APC-Fire space 810. And then at that point, we can run the wrapper function, and it's going to return to us that name list. And that name list will have both various data frames and various plots that we might be interested in seeing in a single go. The ones for this one include the linear slices, but you can also see cosine similarity, the individually normalized signature plots, the average signature plots, a bunch of this more interesting plot data that might be useful to query. So let's go ahead and check to see what impact it would have had if we had divided everything into 10 percentile bins based on that positive gate that we drew for APC Fire 810. So this one, looking at it right now, is still showing the, I think this is the normalized data. So if we look at the very brightest bins, so anywhere from 90 to 10%, this is what the signature would have been. versus if you're gating the dimmest 10%, you would have seen a signature that looks like this by comparison. So there is a little bit of difference in the signatures based on where we're drawing those gates in terms of, looks like the violet 7 detector and maybe a little bit on this R1 detector. But ultimately, an interesting thing to note is when we include everybody, for those little bit of autofluorescent detectors, you can see there's a little bit of step ladder appearance as you start including dimmer and dimmer cells into the overall signature. So, back in our Cyto 2025 poster, and also the talk, what we ended up kind of tracking down for this little step ladder appearance is this is likely leftover residual autofluorescence that ends up being incorporated in the signature. The reason for this little bit of leftover residual autofluorescence is that not all cells are equally bright for autofluorescent molecules to exactly match what we see for our autofluorescent signature. Some are going to be greater, some are going to be less, and then at that point, when you're getting on those dimmer cells, some of them are going to be greater, some of them are going to be less than the average background that gets subtracted. Now, if you're subtracting out a background that is actually going to be brighter than what is present for those individual cells, those cells will end up with negative values. However, if you're subtracting out the average background that's not actually matching the full autofluorescence that's present on those individual cells, there'll be these little bits of residual that are left primarily around those peak detectors. So, when you're gating on the dimmer staining cells for your particular fluorophore, the relative proportion of those autofluorescent leftover peaks to the overall signature are a greater proportion, so they contribute more to the final version of the signature. By contrast, when you're looking at them in terms of the brightest peaks, the ones where it's so bright that any little change in autofluorescence is basically negligible, you're not going to see much change across the board for those two. So that's what we attributed the step ladder appearance to actually be appearing as. However, in this case, this was relatively minor for APC Fire 810, but for other fluorophore antigen combinations, it can be quite dramatic and can make up quite a bit of the overall signature, which in turn will substantially impact your mixing, as we showed for that poster. So in this case, this was an example for this exact same data set. We had been using BUV615, which was CCR4, and then PSI5, which was CD25, as cell controls initially, but we're having some major unmixing issues. But then we noticed it's like, even though we were following best practices as far as the application of our positive gates, and we thought that, yeah, this looks like a good gate for cell controls, when we actually looked and see the same kind of approach, we could see that no matter how we drew the gate, even if we were drawing at the peak and then over, we had about a significant amount of residual autofluorescence that was creeping into the signature, increasing the similarity to other fluorophores that were similar to autofluorescence and causing a bunch of unmixing issues. This in turn ultimately was fixed when we ended up switching from these cell controls to bead controls to be able to avoid having accidental little bits of autofluorescence end up in those signatures and cause issues across the board. Alright, so far we've looked at normalized fluorescence signatures that have been based on a gating region of cells of interest that we then gated for being positive for a particular marker. Or alternatively, taking that same area, dividing it into 10 percentile bins, and then checking those bins for the same kind of signature. So both of these approaches are functionally essentially the same. We are taking a median measurement of the cells that are present for a particular region and deriving out the signature values. However, as in much of science, there's a lot of additional information that can be gleaned beyond just looking at the average assumption, and this is also the case when it comes to signatures. So we could gain a lot of additional information both about our single colors, how our antigen fluorophore combinations work in context of our cells, and also the quality of our fluorophores in terms of the current status of their vial if we were able to look at the normalized signatures that are present on individual cells. So the main focus of the Lucianaga package is being able to implement this kind of style analysis. A lot of this is being done via the Lucianaga QC function, which has like its own entire article within the package vignettes. But what we can end up seeing is this, how this actually will work in practice is if instead of gating for your region of interest, retrieving an average signature, subtracting the background, and then deriving the signature, if instead you were working at the level of individual cells, you could identify what the primary peak detector is, subtract out the autofluorescence background, And then once those autofluorescence backgrounds are subtracted, you're just left with the individual fluorophore contributions of those individual cells. At that point, you could then normalize, and then once everything's been normalized on an individual cell basis, aggregate them together on the basis of shared peaks of relatively similar heights. You could then return this as a data frame to be able to use for different things in R, or alternatively, isolate out the cells that share these unique signatures that are just different in terms of brightness so that you can use them for use in unmixing. So the visual aspect of what this process is just like here. Basically, you identify that peak detector, you subtract out the background, you go ahead and normalize the individual cells to get out its individual normalized signature. You identify where the peaks in the particular fluorophore are, and then you aggregate cells that share those same peaks of relatively similar heights to be able to get back out relatively pure signature populations from your general unmixing control. And what we've ended up seeing is this is quite useful in terms of identifying when your fluorophore is having tandem degradation occurring, as well as being able to isolate out rare autofluorescences for use in unmixing. So, a lot can go into all the finer tuning of these details, but for now we're just going to use the course wrapper for the Luciérnaga integration, using the same lines of code that we had above to be able to get at what the view of, instead of looking at the average, is in terms of looking at the individual normalized cell. So if we go ahead and check in with our returned list object, there are various style outputs. So if we were looking at it in terms of the individual normalized signatures that then got aggregated together for our APC Fire 810, right off the bat, we can see there's a lot more dramatic changes in terms of the signatures that are present for our particular gated region. So everybody still shares this R8 region, but we can see there's a substantial change for the R1 detector, ranging anywhere from maybe 25% of the peak as far as the peak detector. So this is a 0.25 value, all the way up to nearly being co-equal in terms of emission with the peak itself. And then we can also see those little bit of stepladder appearances appearing for where we expect to see autofluorescence. So right off the bat, there's a lot of variation that's being present, and it's once again in those two detectors that we could not subtract out with the background autofluorescence, namely the YG4 and the R1 detector, which are also contributing to the main difference in our signature compared to the reference signatures available from other sources. So, we still need to try to figure out exactly what's going on with those two. So, what is happening in the case of this particular cell single color control? So, if we pull up the reference signature for APC Fire 10, but also for its parent fluorophore APC, we can start seeing some very interesting patterns. So this is via the QC reference library to pull up the reference signatures for both. And as you can see, APC Fire 810 is supposed to be at R8, but then we can see for APC, the detector's at R1, and it's also at YG4. So it turns out that signal we've been seeing fairly consistently in the averaged view for APC from R1 and from YG4 is actually due to APC being present. And given that this is a tandem die that has APC conjugated with the Fire 810 component, it's likely APC Fire 810 for this particular fluorophore or for this particular single color is degrading back down into APC contributions. And then these APC contributions end up giving the overall brightness to the R1 and IG4 detectors, and because it's happening to a greater extent, we're actually seeing it appear in the overall signature. So it's clearly not completely degraded all the way from APC Fire 810 all the way back to ADC, because the R8 detector remains the primary detector, but there is a lot of co-expression of different things that have APC Fire 810 versus things that have APC on the individual cell basis, which is why we see that stepladder appearance when we run it through Luciérnaga. So it's visually striking, but we also have to remember this is rather sensitive. So if a single cell has a different signature, it will also be plotted in the same kind of wrapper view. So we should try to see what the actual proportion is in distribution, because if it's just 3 cells have these weird signatures, but everything else remains the same, we don't have to worry about it. We can continue doing a regular style gating to get at our underlying signature. So One of those other returns to the named list is the proportion plot. So we access the named list through the use of the $sign. We can grab it, and then we can pass it to Plotly. And we can see that things that are relatively dim in terms of the R2 detector, which is similar to R1, there's very few cells that don't have any APC contribution present at this point. But then we have a good chunk of cells that are somewhere in the middle, with the R2 detector contribution from APC ranging from anywhere from 30% of the peak detector to like 50% of the peak. This looks to be about 70% of cells are somewhere in this intermediate range, but then cells that have a severe amount of APC present on the surface are maybe another 20% of cells. So substantial enough that we're able to see it across the board. So at this point, it's worthwhile to step back and think about it. So the antibody fluorophores that we're adding to our single color controls can be exposed to reactive oxygen species that may degrade that individual antigen fluorophore before it ends up binding to the surface of the cell. So it's not necessarily happening at the entire level, like if you had added bleach directly to your antibody vial, but it's one of those situations where you might have a situation where on the cell surface you have co-expression of both intact APC fire 810 as well as severely degraded back down to APC fluorophore or some mixture of the both. Ultimately, depending on your antigen density on the surface of the cell and the titration that you did with your antibody, you'll have different extents of the R1 and R2 peak detector, which is what's getting captured by the Lucianiga integration function in that view of the plot of the individual cell normalized signatures that got aggregated together. So, if you want to see a combination of both the proportion and different signatures in a single view, this would be the amalgamate plot, which is also returned from Lucianiga integration wrapper. So we just need to access it through that part of the named list, and it will give you a little bit more of that same kind of visual summary where we can see these are all the variants of the signature that are present for our gated region, but at the same time we can see that the average measurement that would have been taken if we just grabbed the entirety of the gate would have been somewhere around here. So this is the one I will tend to go and use when I'm screening my reference controls to see if I'm having any issues, just because this is the more useful one of the bunch. And similarly, in terms of name syntax, just remember the first detector mentioned is the peak detector, second detector mentioned is the second brightest detector, and third detector mentioned is the third brightest peak. So as you can see, R8 as a primary has a value of 10, R2 has 90%, and YG4 has 50% of the peak detector. Now, if we go ahead and double check this, against this was using guessing what the similar fluorophores might be in terms of identifying our mystery candidate. We can see our version still is very different from the reference APC Fire 810, and we can compare it against all these other fluorophores where they are not degrading, they don't have this APC contribution across the board. So this is a little bit of a prelude when it comes to next time when we are going to be looking at how to generate a cosine matrix to be able to compare fluorophores against each other. But this also is also present as one of those wrapper returns, so it might as well look at it. So if you're thinking about when this particular fluorophore is degrading, what should I provide in terms of the actual fluorophore signature to get the best unmixing results? You can see that these signature variants are kind of a little modal. So if your cell has a fluorophore signature on the surface that looks similar to this, they're going to unmix relatively well, versus if they're over here in this quadrant and they have that severely degraded signature, they're not going to unmix whatsoever in any pleasant manner for that particular fluorophore. So, at that point, we have looked at the cell single, characterizing individual normalized signatures of individual cells. The question that you may be having is, this was done for cell single color controls. Can we then use this also for the unstained cell controls to be able to isolate out rare autofluorescences that may be hiding within the average? And the answer, of course, is yes, you can. Obviously, you'll still need to load in your cell unstained gating set intermediate to make sure it's available in your environment. And then the main thing to be able to use Lucianiga integration wrapper on it is you need to provide the unstained argument is true so that it won't try to subtract out backgrounds from everything. So this is what it looks like in terms of setup. We're just going to go ahead and check this cord blood mononuclear cell that we're looking at. And we can go ahead and run everything through Plotly just to make sure what it looks like. So if we're looking at if we had gated differently on a different brightness of signatures, you can see it's not making much of a difference on the overall result. But then if we wanted to go ahead and check to see what the individual cell signatures look like in comparison to each other, we can check that Lucianic QC output. And as you can see, once I'm able to zoom out, everything looks vastly more fuzzy when in terms of the autofluorescence. So actually, let me zoom in for this one. So as we can look and see at these individual ones here, you can see almost everybody has the V8 detector as the main autofluorescence. They have a little bit of difference in terms of shoulder for V5 and V10, but there's actually quite a bit of variation for that relatively good cleanup gate we did on the CBMCs in terms of the expression of whatever autofluorescence molecule causes the UV7 peak, and a good amount of variation when it comes to that blue tree peak, where some of our signatures are going to be primarily the violet 8, followed by blue, followed by a dimmer UV peak, but then some of our signatures are going to be primarily violet 8, and then almost co-equal UV7, and potentially a substantially dimmer blue peak across the board. So this is part of the reason why there's always so much spread present for a lot of our unstained parameters when we're including them within the reference matrix. It's because autofluorescence is not an individual fluorophore, it's a mixture of both of them that you're just taking the aggregate from. And ultimately, if you were using autofluorescence average signature that was substantially different from what was present on that individual cell, that individual cell could potentially unmix incorrectly, not only for the autofluorescence, but also for fluorophores that are similar in those areas of discrepancy where they're being encountered. So once again, let's check the output to make sure that the proportion of these cells, where's the actual running average as far as the individual cells, where are they mostly expressing. So if we go ahead and check, we can zoom in and see that for the main autofluorescence, it seems to be violet 7 as the peak, blue tree around 50% in the peak, and then UV8 a little bit dimmer. And then this will vary a little bit across the board just based on the settings that we ran. Yeah, across the board is fairly common. So, alright, so ultimately with these cell signatures, what I ended up encountering for the entirety of the data set that's now available in SDY 3080 is that some of the cord blood specimens had secondary autofluorescences that were primary UV8 peak detectors, and that when these were present, they ended up causing substantial unmixing issues, even when these cells were relatively rare. The actual details you can find at the poster PDF that's attached in the link. So let's go ahead and visualize the proportions in the form of that amalgamated plot. And this is the one I really like, because you can see what would the signature have been if I used the average, what would the signature be on the individual little cells, where can I maybe consider adding in a second autofluorescence, which I probably would have added here, except in having the blue tree, if I was trying to have better resolution overall for my panel. And then if you're running the full fine-tuned option, it can also return the purified out cells that are positive for this peak for use in unmixing as well. So please note, in our experience, those quirkier mixing errors tend to be tied to those individual cell autofluorescences, primarily in the UV8 and the blue tree region. And we will revisit this topic and try to see how our different decisions have on the final version of our data in a couple weeks when we go through the unmixing walkthrough. And just to prevail next time in terms of signature comparison, let's see what this would have looked like in terms of cosine value or similarity value if you're on a Cytec Aurora. You can see most of the autofluorescences kind of fall within this norm, kind of similar other ones stretching out a little bit, and then there's some of those rare individual cells that will always unmix incorrectly no matter what you do, just because they're so different from everybody else. So, as it turns out, as we suspected, it's not just a single autofluorescence signature when we're gating on relatively healthy PBMCs or CBMCs, so it's no wonder when you encounter random specimens that have unmixing patterns for what seems to be relatively small populations for specific markers. It's just a little bit of uncertainty being introduced in other ways, which is being captured when you do the unmixing there. Alright. So today, in this primary course material, we did the walkthrough process by which we extracted normalized fluorescent signatures for our mixing controls, both single color and unstained. However, as it's not lost to many of you, we have been here for an hour and 45 minutes, and we've only really gotten through one fluorophore. There are over 28 remaining fluorophores to go just for this panel. Do you need to repeat all these steps for all the above code above? And until recently, the answer would have been partly yes. You could have scaled up and made things a little bit easier, where you would have had to assemble this first initial script and then just basically rerun the script on a per panel basis each time, making adjustments as need be. However, with those recent changes that were made to both the Flowgate and the Lucianaga packages, a lot of these really painful areas as far as like the implementation have been written out as code functions that you can then just be able to use in a single go, have you do all those initial setups similar to what the commercial wizard would have been doing, so everything becomes much more simpler to do and you can carry out the same process in parallel and have everything done within 10 minutes. So this actual process, as far as what we end up seeing, is documented within the bonus walkthrough material, specifically the signature matrices, a walkthrough, and basically using these functions by modifying the template just a little bit, you can have it iterate through all the different steps we did individually today, and this more detailed, looking at all the individual steps present, can be done by the function itself in the background. So ultimately, when you do run it through and then you get back all the return signature matrices, this is what this looks like. So we do get back values for the cells, and then when we end up plotting for this particular data set that we end up grabbing, if we go back down here and check for APC Fire 810, right there, and then for APC Fire 750, you can see that this is what our signature looks like for both APC Fire 810 and 750 for when it's derived from cells. We see this amount of autofluorescence contribution that we were not expecting to have. But then vice versa, we can repeat that same process for beads in 10 minutes. And then at that point, if we're comparing what we have for beads, and let me zoom back a little bit. If we're checking at that point for APC Fire 810, you can see the bead signature was relatively clean across the board, and the APC Fire 750 signature was relatively clean across the board. Which is interesting because these were both stained within a couple days of each other from the same vial, which suggests the tandem degradation that we're seeing is not really happening at the vial level, meaning we need to buy a new APC Fire 810. It's likely whichever cell is bearing that CD38 expression is producing reactive oxygen species, which is causing the degradation of the APC Fire 810 on the surface of that cell. So always something that you can glean from this little bit of information from single colors that wouldn't have been available to you otherwise if you haven't started learning how to use R. So ultimately, once you have those signature matrices, you then are able to do comparisons with them, as we will do next time, as well as use them to unmix your raw full stain samples, as will be covered in a couple weeks. So our takeaway, over the course of this walkthrough, we have started with the setup that we needed to clean our gating sets in order to get at the cells, to retrieve the best signatures that we're able to do to avoid additional interpretation challenges. From there, we learned how to retrieve the cytosets for the gated cells, to retrieve the X-ray matrix, and to also isolate out the fluorescent detectors. At that point, we then orchestrated our way through summarizing the median, the background extraction, and the normalization. We learned some new functions to be able to visualize the signatures, both raw and normalized, and use them to screen to see what was going on with our APC Fire 810, so that we could better plan for our individual experiments. We also did a little intro to the Lucianaga integration wrapper function to be able to glean a little bits of information about tandem degradation and autofluorescent variations from those same gates without needing to do the full Lucianaga pipeline and play. So overall, I hope this walkthrough, despite its length, has been helpful. I would like to end circling back so that we can recontextualize what the community as a whole, through various different means over the years, has converged on in terms of best practices for single color and mixing controls. So if we think about the first rule, it tends to be something along the lines of single color cells need to be as bright or brighter than the full stain sample. So just from what we were playing around with today, we can see that when we divvy things up by percentile, we observed that the antigen fluorophores that had thinner staining combinations ultimately had a greater proportion of residual autofluorescence that ended up contributing to the overall signature, which would also explain why when you were gating broader like that, you ended up having issues with your unmixing. Similarly, what we encountered for APC Fire 810 is that for those cells where a lot of that APC Fire 810 ended up being degraded back down to APC, you're more likely to have the APC contributing to the overall signature, increasing the spread to other similar markers, causing extra issues with your unmixing across the board. It still, however, leaves open the question of why, when you're mixing with beads that are only as bright to 10 to the 4th, but you're mixing with fully stained cells that are up to 10 to the 6th, you can get unmixing issues, but that's a problem for a different day. For the number 2, remember, it's something along the lines of make sure your autofluorescents are matching for your positive staining population as well as your negative staining population. So as we saw today, there's substantial variation in terms of both brightness and signature, even for cells that are gated in the same similar region. This makes sense because autofluorescences are combinations of biological molecules that get averaged out into kind of distinctive shapes. As soon as you activate or you insult the cells in any way, the relative ratio of these molecules may shift, the signature may shift, and you may have a new variant that you need to account for. And then likewise, if you don't correctly extract out the correct amount of background, these leftover residual autofluorescents can then be incorporated into your overall fluorophore signature, which will complicate analysis downstream. Rule number 3 is basically use the same fluorophore. So beyond not substituting in a BB510 using Zombie Aqua, which is what older PIs will tend to suggest to new users that are FluoCore, which I then have to correct, we did observe a lot of variation for APC Fire 810 in terms of tandem degradation, which opens up a bunch of questions we'll try to tackle over the next couple sessions. Namely, is it better to use the degraded tandem as is, or is it better to use a proper APC Fire 810 in terms of being able to use it for mixing? But what happens if you have an APC already present in your panel? Are you misattributing cells that are being as CD38 for whatever the marker APC is bearing at that point? And then how can you glean that bits of information from other people's panels that may be available in a general data repository? So more questions than answers at this point, but fascinating nonetheless to be able to investigate. And then, obviously, you need to have enough events. As we saw for the fuzzy individual cell normalized signatures for autofluorescence, our cytometers are noisy. A bunch of this variation is likely just the cytometers causing Poisson noise. It's not necessarily the biology. But the more events you're able to acquire, the more these signatures get smoothed out in terms of sharp curves, and the more confidence you may have. And we will revisit some of these points and try to answer some of these questions as we move through the next couple sessions, as well as the bonus material. So until then, thank you for persevering through my spectral signature nerd out. Next time we'll be looking at signature comparison, as well as how to build unmixing dependent spreading hotspot matrices, or collinearity, depending on which paper you read recently, and all the other fun ones in terms of comparison across the board for your panels. And that's all I have for today. So additional resources, unlike the last couple sessions where it was very much topic specific, additional resources kind of will overlap for this particular section, because generally something that's going to be good talking about spectral signatures is also going to dive into comparison, and it's also going to go dive into unmixing in a similar paper or talk. So here are a few of the exceptional resources that came to mind as I was writing this. It may not necessarily be entirely applicable to spectral signatures, but it's what I was thinking of at the time. So obviously any of Peter Mage's talks will be good when it comes to understanding and mixing. So both his flow text talk from last year as well as the Cytometry short tutorial are where I'll reference you for the first ones. If you go back and revisit University of Chicago Flows, Laura Johnson's videos on advanced and mixing, everything was done on a Cytec Aurora at the side of the software. But now that we've played around and tinkered with all these different parameters individually in R, it's a very fascinating rewatch seeing how her decisions end up impacting things in a similar way to what we have encountered for our own fluorophores throughout our different flow cytometry careers. And then ultimately, David Novo's papers are always a good place to go to try to understand the actual things that are happening in the background when it comes to spectral signatures, mix-mat, all the other caveats. I still have math panic even to this day every time I start a new paper and I run into a new equation, but a lot of what you need to understand it is in the paper itself, so I'm always appreciative of them, and they have helped solidify a bunch of these concepts as well. The take-home problems for today, everything we've worked on so far was mainly that APC Fire 810, so pick your fluorophore, pick your antigen, kind of do the same kind of deep dive, see if you find anything interesting, any new autofluorescences, or any new tandem degregations across the board. For number 2, we often were gating as bright or brighter. Go ahead and re-edit the gate we have within FlowGate, make it to include the negative cells that would, the dim positive cells that would more have likely been autofluorescent, non-specific staining, see how that would have impacted the overall signature. And then for number 3, as we saw, background subtraction can be important, especially for some particular dimmer antigen fluorophore combinations. So go ahead and see for our 3 cell unstains, which were different individuals, contributing those cells, and they were treated under different conditions, if we had used those to do background subtraction on our given fluorophore, if it would have affected the overall signature that we would have seen. So all three of these are not necessarily meant to be challenging, they're more meant to be figure out all these little bits of the workflow and actually get comfortable using them so that you can apply them to your own projects in well in time. And with that, that's all I have for you guys today. I'm around if you have any questions in the chat for a few more minutes. And if not, if you have any questions or any issues that arise when you're running data for your own spectral flow cytometers, or if you also encounter that ggcyto reinstall bug, reach out on the forum and we'll try to navigate that this week to make sure it's up and running for next time. And with that, thank you for your attention.